Alright, so this is a recording of the 3x3 carry look-ahead adder, and I am going to pretend that I'm a student and see if I can follow my own instructions. Alright, so question number one says, we have to create a circuit with these input pins and also these particular tunnels, and it specifically say that X and Y are 3-bit input pins and K0 is a 1-bit input pin. On the right, X, Y, and K0 are tunnels. Note that tunnels also have a bit width specification. In order to connect to a pin to a tunnel properly, the two must have the same bit width. Look up the library reference of tunnels and so on. So the correct answer here is the name of the tunnel is displayed as a visual label, but it also identifies connectivity between individual tunnels instances that have exactly the same name, so they're basically logically connected. It does not connect to other components of the same name, and the label is not only used when the circuit is printed, it is actually having the other purpose of making a logical connection. Alright, so having said that, let me start up Logisim so I can actually do some work here. Alright, so that's not working. And let me see where the command really is located. I thought it was here, but it's not. So maybe I can just start it from anywhere. Nope. Nope. So I can't remember where I put the Logisim command because I just wrote this shell script for that. That's okay. I mean, we can always start it like this. There we go. Alright, so here's Logisim, but you can't really see the entire thing. So I'm going to have to resize it so that you can see the entire Logisim. Give me a second here. There we go. And I think that's about as large as you can go. There. Alright. Alright, so I'm just doing exactly what you need to do for this assignment. So we have a pin called X, and uppercase is fine as long as you stay consistent with that uppercase. But I should probably refer back to the diagram here and see whether it is lowercase. So this one is lowercase, so I'm going to stick with lowercase because in Logisim everything is case sensitive. So that's why it is important to kind of observe the casing in the lab instruction, because otherwise certain things won't work. And quite a few people turn in the circuits with the uppercase K instead of lowercase k, and that didn't work in the test driver, and I had to manually go in to find out what's wrong or why it is not working. So I think in the future it's probably important to keep an eye on all the casing. Alright, so here we have the tunnel, and I also want to make sure the tunnels are actually uppercase. Okay, fine. So we'll use uppercase for the tunnels. So here's X, duplicate it, and here is Y, duplicate it, and here's K0. Alright. And then after that we have to change the number of bits or the bit width, and both of X, Y are supposed to be 3-bit wide, and then we make the connections like so. So we can see there are no errors because they all of these components that I'm connecting, they all have the correct bit width. Alright, so this part is done, and it's time to move on to the second part. Alright, so the second part, now use the following as a starting point of another part of this main circuit. So this is not another circuit, this is another part of the same circuit. So that means we are not removing or changing any one of these, we are just simply adding some additional stuff here. Alright, so we got X, Y, K, 0, we got these gates here, and we also got P, G, and Q over here. Note that the direction phasing of the tunnels can be changed as like most components. Also note the size of the gates and the number of inputs of the gates. The gates next to the tunnel on the right hand side may not be the correct one for that particular gate. In other words, the positioning of the gate and the tunnels do not necessarily indicate the correct association. Yada yada yada. So that means you really need to know what is P, what is G, and what is Q. And at this point of the class, I think it is super important to understand at least where to find the definitions of these bits. And obviously, you can use the text if you need to figure out how those particular bits are defined. When this is done, use the poke tool. Okay, so let me hook it up first. Alright, so I am going to be a little bit on the lazy side and just duplicate these three, put it down here, and then flip the direction of all three at the same time. Alright, so yeah, that's a lot faster, right? And then we go for the logic gates, and those are under gates right there. So we have, let me see what the order is here. So we have exclusive OR, and AND. Okay, so we have exclusive OR, and then we got a regular OR, and then we got a regular AND. There we go. Alright, so I'm just going to change all three at the same time, in terms of the number of data bits, as well as the size of the gate, as well as the number of inputs. There we go. So you can see, understanding the user interface can potentially really help to get things done a lot faster, which is, kind of important sometimes. Alright, so on the other side, we got 3 gates too. So I'm just going to do some duplication here, stash it on this side, flip the direction like so. And I have to change the name because this one is supposed to be, okay, let me check the notes here. PGQ. Okay, there we go. So this is supposed to be P. This is supposed to be G. And this is supposed to be Q. There we go. Alright, so the way P and G are defined, I specifically said in the class that it is it's defined in a paragraph, and it does not seem to be important, but it really is. So I already told everyone to highlight it, using a highlighter, or just copy it in your own notes. Excuse me. Do whatever you need to make sure that you can find it. So P is the disjunction. Yes, it's the disjunction between X and Y. So we're gonna put connect X on one side, Y to the other side, and that's P. G is the conjunction, so we just need to take the conjunction, and I did not plan very well, so I need a whole lot of zigzagging here, but it still gets the job done, so it's not a big deal. It's just that the circuit may not look as nice as it could have been, and because these are symmetric, so it doesn't really matter which one goes to the top pin, which one goes to the bottom pin. So there we go. And then whatever is left is Q. Q is the exclusive OR. Oh, okay, never mind. I made a mistake. Sorry. So I made a mistake here because G is supposed to be the conjunction, right? that is exclusive OR. So that's my mistake, and I did not plan very well. So I need to move this one. Let's see. We will just go ahead and do this. I think that will save our day. Okay, we'll see. So there we go. It is the output of the AND gate, but we are still feeding X and Y to the AND gate here because G is X and Y for each of the bit position. And then the last one is Q, and yeah, it's gonna look kind of ugly because Q is the exclusive OR between X and Y. So as I mentioned earlier, by this time it is important that we at least know what the definitions are, and understanding why the definitions are the way they are is also important, but knowing is the bare minimum at this point in this class. Alright, so getting back to the question. So I'm supposed to specify 001 to X, 101 to Y. Alright, so we switch to the poking tool, 001, and then 101. And then, okay, so I made a mistake somewhere in the circuit. Alright, so what did I do here? The AND is correct, but then the OR, the exclusive OR, is not. Alright, so we have to get rid of this wire. And get rid of this one. And that was just because I was doing it in a hurry. And Q needs to be a 3-bit tunnel, not a 1-bit one. So, because there are 3 Q bits, Q0, Q1, and also Q2, so that's why. Alright, so now that I got everything here, I can now switch back to the poke tool, and I'm supposed to poke what? So it says right here, now use the poke tool to click the wire connecting to the tunnel labeled Q. What is the second number to the right hand side of the slash? Alright, so let's click here, and it's -4. Alright, so we just put -4 here, and then we move on to question number 3. So question number 3 says, now you have all the bits needed to compute the carry bits. Let's start with a new circuit K1. This means you need to use project, add circuit, blah blah blah. So this is basically just, you have done this stuff already in the past. So it's just creating a new circuit. To make the main circuit simple and clean, use multi-bit input pins P and G in the K1 circuit. You will also need K0 as an input pin. In order to make sure this circuit can be tested using a script, make sure that the relative vertical position of P, G, and K0 input pins are as shown. Quite a few people did not do this. Okay, so please read the instructions carefully, because otherwise points will be deducted. And I know some people are just saying, why would I get points deducted when my solution is actually logically correct? Because it's not following the instructions. It's kind of like you're buying a thumb drive, okay? So the thumb drive is supposed to come with a USB-A connector, but they ship a product that has a USB-C connector. Can you just say that, well, I guess it's kind of the same thing, even though it doesn't plug into the computer or the device that I'm planning to use it for? No, you'll be upset, right? Because you did not get what you thought you bought. So it's the same thing here. Okay, so please follow the instructions properly. I only took off 1 point for all of these minor mistakes. Well, it's 1 out of 4, but it's still something that is completely avoidable. And then on top of that, the test driver would have detected these mistakes as well. So so people who got points deducted, well, 1, make sure you read the instructions, and 2, try to make use of the test driver, because that's the whole purpose of the test driver, is so that you can detect problems with your circuit before you turn it in. Alright, enough preaching here. So now let's go ahead and create that circuit. So go to project, add circuit, and this is going to be K1. Once again, case sensitive, so it has to be lowercase k. There we go. And then we have 3 input pins. I mean, if you're lazy like I am, let me show you how lazy I can be. Alright, so you can go back to main. Main already has the same kind of width of input pins. So what you can do is to copy this, Control C, go to K1 and paste it. It's just that this time you have to make sure that this is no longer X, and this is basically P, and this one is no longer Y, it is G. There we go. And then you have one single output pin, which is also a 1-bit output pin, and it is corresponding to K1, so let's call it K1. Okay, there we go. So now we have to convert the Boolean expression into the gates that we need to put here, and I can never really remember those equations or the formulae, even though I can derive it, but I cannot remember. So that's okay. I mean, you're allowed to look up the notes here. So we'll go ahead and look up the notes. So let me go back to the class, open a new tab, and then we look up binary addition, or just binary number addition. There we go. So now we get to the notes, and then we go to section 6, where it does define how K1 is defined. It is G0 or the conjunction between P0, K0. Alright, so I gotta say this right now at this point. If I were a student in this class, I would have copied this equation to some place in my own notes where it is easy to find. Now, since I'm not a student, so I'm just going yeah, I know where to find it because I wrote this document, okay? You did not write this document, so it is important for you to extract all the useful information to a particular place, preferably before class, okay? But during class is okay too. I mean, if you bring along a notebook during the class time, you go this is an interesting equation. Let me just put it aside and put it into one area of my own notes. That would be fine as well. But you have to find a way so that the equations, definitions, stand out and it is easy for you to find. Alright, so it's G0 or P0, K0. Alright, so let me go back to the circuit here. We know that we need an OR gate and we need an AND gate. That's by the way, that's an AND gate. This is an OR gate, and both of these are ugly and unnecessary and have unnecessary number of pins. So we have to reduce all of those to just 2 pins. Now, if you use more pins, if there are input pins that are not connected, guess what? The output sometimes will not be correct because if there's an input pin that's not connected to anything, how does the gate know what that input is supposed to be? So I saw one person, just one, who did not change the number of input pins, and the outcome did not come out to be correct. I mean, that's just the way it is. Alright, so I think it's G0 is on its own. Okay, going to one of the inputs of the OR gate, and oh, it didn't work. Why? Well, because we only need one of the 3 bits of G. Okay, so let's go ahead and undo this and use a splitter to help us. Now, the grading does not do anything about it's not based on whether your circuit is ugly or not. So it is actually just much more convenient to have every single bit already split out, okay? Because this way I don't have to modify anything. I just have to pick out the right output instead of having to deal with bit 0 goes here, bit 1 goes here, bit 2 goes there. I don't care. I just need to pick out the right one. Alright, so now that this is done, I know that K0 goes into one side of the AND gate, Why do I know? Because you can see how K right here. So you can see how K0 is a part of this conjunction and P0 is the other input to this conjunction. So we pick out P0 to make it the input to this same conjunction. And then the output of the conjunction is one of the input, goes to the one of the input of the OR, because according to the expression here, the conjunction here is the right hand side of this OR over here. So the other component going to the OR is just G0, and now we're done. Alright, so switching back to the instructions, which is here. Nope. Sorry. Nope. Here. There we go. Let me close the one that I'm not supposed to let you guys see. That's going to be this one. Yep. Okay. Alright, so let me see. Where are we? Right. So we are here. And the edit the appearance, so it is to identify PG, K0, and K1. Of course, a bunch of people did not do this, and because if they did, they would have found out that the P and the G and the K0 may not be in the right order. Yeah, so this is kind of useful. This is like commenting. It's basically a second chance to catch mistakes. And when people don't do that, those mistakes goes unnoticed until I grade it, which means points will be deducted. Alright, so we got P, we got G, we got K0, and then we got K1, and now we just have to move these things around so that they are at the right place. Okay. Now, if people don't do this, okay, if your circuit does not have these captions, it's not the end of the world. I mean, I'm not going to take points out, simply because that requires me to take a look at your actual circuit in order to deduct the points. I'm not going to do that. But at the same time, if you don't do this, it would be harder for you to spot your own error. I mean, you can do that, when you run the test driver, but but commenting this, here is just a whole lot easier. All right. So getting back to the circuit here. Oh, okay, fine, uppercase. I mean, it's not super crucial, but since I want to be consistent, there we go, uppercase, there we go. And then we position things a little bit just so that they look nicer. Okay, there we go. Alright, so getting back to the question, so to test the circuit, see that the input pin K1 is the output pin K1 is a 1 if and only if two of the following inputs are ones: K, X0, Y0, K0. So this means you have to connect an instance of the K1 circuit to the main circuit, connect PG and K0 correctly, then use the poke tool to adjust the multi-bit input pins X and Y, or the single-bit input pin K0 to test the output of the K1 circuit. Okay, so what does that mean? Well, that means you go back to the main circuit here, and then you go to K1, because that's a circuit that we just created. So I'm gonna put it here. And if you want to be fancy, you can use two tunnels just for connecting to the K circuits. Okay, because this way your circuit is gonna look nicer. So we make everything point to east like so, and then K0 will also need to be connected. So make another one up here. Alright, so P goes to P, G goes to G, and then K0 goes to K0. That's how we test the circuit from outside. And this bright green here is a 1. So you can see how we have 1, 1 here, and K1 is a 1. If I make K0 a 1, and I make one of the other two a 0, you can see how K1 is also a 1 here. So that's what it meant for self-testing that circuit here. Alright, so going back here, the question here is how many AND gates are needed in the circuit K1 to compute K1. This means do not include the AND gate to compute P, N, or G from X and Y. So there's just one. There we go. Question number 4. Now you can create a subcircuit for, now that you can create a subcircuit for K1, do the same thing for K2 and K3 using their carry look-ahead formulae. Okay, so this is important. Use their carry look-ahead formulae. So what does that mean, right? It means, some people look at this circuit here and go like, can I use P1 in the circuit of K2? The answer is no. Why would I go through this derivation and get to this form when you're supposed to use this? It doesn't make sense, right? And in class, we also talked about, how that is not going to help because it does not change the dependency of K2 on K1 if you put a K1 circuit in order to compute K2. So this is the equation that we want, okay? And that's what we need to do for K2. So let's switch back to the circuit here, and we can just go to project, add circuit K2, remember lowercase k, and then we can copy and paste a bunch of stuff. In fact, go ahead and copy and paste everything, and then we'll just go ahead and change the things that need to be changed. So Control C and then Control V. Okay, I know you guys know how to copy and paste. Alright, so the gates, well, we're going to get rid of some of these gates here. The output is now K1 K2 instead of K1, so change the name accordingly. And then we'll go ahead and also remove these wires, because more likely than not, they're not at the right place, so we'll get rid of those. And now we can go back to the formula and find out what we are supposed to do. So we need a 3-input AND gate for P1, P0, K0. So we go to, we need a bunch of gates. We need two AND gates and one OR gate. So we might as well get that bunch of stuff here, because I know that I want to change a few things. That's universal. One, I want to change them all to the smaller version. And 2 of those are going to have 3 inputs, and one of them will only have 2 inputs. So I have to kind of adjust this one by itself. There we go. Alright. So now the one with 3 inputs is the one I want to deal with first. And that's the one that connects P1, P0, K0. Alright. So we have to be careful. Okay, so K0 is right here already, and then P0 is here. And let's see, P1 is right here. So when you make these connections, you kind of need to make sure that it doesn't cross the connectable pins, because when you see a dot, that means the wires are connected. And I saw a few people having cross-wire issues like that. Alright, so there goes the 3-input AND gate. This is the 2-input AND gate using P1 and G0. So it's going to be this one. So this one needs P1 and G0. Yep, P1 and G0. So we'll connect the G0 right here, right across. And then P1, we can tap it from here. So that looks kind of nice. Alright, so now we need the OR. So we just need to take the output of the 2 AND gates here and then just do the OR, which is just by, and also connect G1 by itself to the OR input. Alright, so here's the OR. I cannot remember which one. G1, there we go. Yeah, I can derive things, but I cannot remember things. So that's, sometimes it's kind of annoying. But that's okay. Alright, so this is all done. This is K2, and I am going to do the same thing in terms of labeling. So we'll specify P, G, K0, K2 this time. And obviously, if people are not doing these capturing for K1, the same people are also not doing this for K2. Alright, so here we go. And then K2 can go here. We have enough space for that. Alright, excellent. So now we can work on K3. So add another circuit. And this one's for K3. And once again, I'm just going to do some copy and paste. So we can copy, go to K3, double click when we want to edit the circuit. And then this time we also have to remove a bunch of stuff. So this time I think I'm just going to remove the wiring and kind of try to keep the gates around, because many of the gates I can kind of keep. It's just that the way they're connected won't be the same, and the number of inputs may change a little bit. So there are certain things I have to adjust. But for the most part, these gates can still be here because I still need a 2-input AND gate, a 3-input AND gate. It's just that this time I also need a 4-input AND gate, as well as changing the OR gate to 4 inputs. So there we go. Change this to 4 input, and then make a duplicate of this. Control D makes a duplicate, and change this one to 4 input. So there we go. So now we got all the basic gates. We just have to figure out what goes where. So now we look at K3. Once again, do not use this one here. Okay, there's a reason why I derived it all the way to this form. Use the most expanded form. I think I even talked about it in class, but some of you may not be paying attention in class. But if you read the notes ahead of time, that would kind of serve the same purpose too. So it's kind of cool that way. Alright, so we need all the P's and the K0 for the 4-input AND gate. Alright, so in that case, it kind of makes sense to make the 4-input AND gate all the way up here, because it's easier to get all those wires connected to this one. So, this is P0, P1, and here's P2. It also needs K0. Alright. So there we go. One of the AND gate is done. Alright, the 3-input AND gate needs P2, P1, and a G0. So that would be this guy, 3 inputs. And because it needs G0, I guess I can put here. Alright, so now I have to be careful, with how to connect the wires. Alright, so it needs P2, P1, and G0. So this is P2. Alright, so let's hook it up here. This is P1. And then this is G0. There we go. Alright, so that's done. And now we have the 2-input AND gate, which only needs to connect to P2 and G1. Alright, so P2 is this wire, and we can just alright, so let's move. Okay, so this is a mistake, because I basically cross-wire, connected in the cross-wire way. So I have to get rid of that, and then P2 is right here, and it goes to this input, and then G1 is right here. And right at this point, I think it's kind of important to emphasize that a lot of the logic sim techniques that we have learned earlier in the semester, they all come in handy at this point. So so that's partially why I made the announcement, to remind people, okay, you need to kind of brush up on your splitters and your multi-bit gates and so on, because we are using that, not in this diagram, but in main we were using multi-bit gates. So the meaning, or what does it mean to have a multi-bit gate, becomes important. Alright, so we got the AND gates all done. So we have one 4-input AND gate for this entire conjunction, one 3-input AND gate for this conjunction, one 2-input AND gate for this conjunction, and then we can now feed the outputs of the 3 conjunctions and the G2 to the OR gate. Alright, so that's not too difficult. Okay, it's just a matter of how much effort do we want to put in to make this look nice. So I used to hand route circuit boards. So if I need to, I can make things kind of nice and have as little crossover as possible. But since this is just a schematic, it doesn't really matter. Alright, so this is all done. This is my K3. So go back here. This is not entirely necessary, but as I said earlier, it's not a bad idea. Okay, so we have P, G, K0, and this time we have K3. And then the labels are not meaningful from the perspective of how things are connected or how this circuit is being tested. So I can just, the placement is, as long as they're at about the right place, it's good enough. There we go. Alright. So as far as this particular project is concerned, this is all you need. I mean, now it's time to save the project. I mean, if you want to test the whole thing, sure, you can slap a K2 here, and a K3 here. But that's not necessary to use the test driver. So I'm going to save the file. Okay, so we'll go to save. And I also want to follow the instructions, okay, because the instruction has, it indicates what we are supposed to do. So now that you can create, and you can see these are all lowercase too. So yeah, next time, pay attention to the casing. Alright, so once you have the K values, what else do you need to compute the sum bits? So that depends on how the sum bits are defined. The S bits are the exclusive OR. Basically, it's the OR function applied to the Q and the K. So once we have the K's, we still need the Q's. So click this one. Alright, so optional step. Okay, so even though it says it's optional, it means if you do this, you probably will be able to spot your own mistakes. And as a result, it's probably a good idea to do that. Okay, because otherwise, if your design does not work, how can you tell that it's not working? Alright, so we're going to call the circuit 3x3 adder.circ, and then you're free to use whatever file name, right? So you're not required in this case to use 3x3 adder, but in the optional step, it says right here that you need to, it would be handy to use 3x3CA, see right here, or you can copy your own file to a file named 3x3CA. And earlier it says you can save it to any name, so you might as well just save it as 3x3CA. So here we go. Excuse me. Alright, so where am I going to save this? Here is not a bad place. So let me just see. Yeah, okay, I can put it here. So 3x3ca.circ. Okay, so save. Alright, so once I have saved the file, I can get out of the GUI Logisim, because I can now run the test driver from the command line. So the command line, an example of the command line is given, but for the most part here we are basically doing the same thing as the first two assignments where a test driver was also provided. So now we have to say java-jar, where we can find Logisim. There we go. And that's what the /path/2 means. It's basically just saying okay, substitute that with the actual path. Okay. So with that done, we are going to have to go find test driver 3x3CA, which I have not downloaded yet. I'm actually quite surprised by how many people do not know how to download a file from a link. So the way to do it is to right click and then click Save Link As. Now it depends on which browser you're using. I think in some other browsers they might refer to this menu item as Save File As. Or there may be some other, names for this, but basically that's the whole point. I mean, it's save link as, or save file as, is how you can save a file. There we go. So we click that, and I can stash it anywhere, but stashing it in the same folder, that I have C3x3CA, it makes it more convenient. So I'm gonna save it here, and it's gonna replace the one that I already have here earlier, which is okay. Okay, so we'll go ahead and replace it. And switching back onto the command line, I'm going to try to follow my own notes here. Okay, so I already got the first part here. I already got the path to logicsim310.jar, and now I have to specify where to find test driver. It's in the same folder, so that makes it kind of easy. Or not. I thought I put it in the same folder. Maybe I did not. Oh, okay. So I put it into another CISP310 folder. It's actually here. There we go. Alright, so now we also need to specify -tty table. And if it cannot find 3x3CA, I'm going to have to help it find it. Nope, it found it. Okay, so we got the output here. So now we have to compare the output, and the instruction here also specifies how to do that. You may also want to redirect the output, Google, and find out how to do it, but we have done it in the past already, so you really do not need to look up in Google if you have written some notes as you found out how to use the test driver from before. So we want to redirect the output to a log file, so we'll call it 3x3ca.log. Alright, and now here we have the correct output, so we're going to download this one too, so save link as. And be careful where we put it to, because so it is in right under my home folder, not the one under the documents folder. Okay, so I got a few places to stash my files, and sometimes I cannot remember where I stash it. So now we can do a file compare. So in Linux, you can use diff, which I think is a great tool. So I'm just going to use diff to compare the log file that I just downloaded, which is under CISP310, that is under my home folder and not in the documents folder. And the name is testdriver.log. And then we have to also specify this log file that we just created, which is 3x3ca.log. And if diff does not have any output, that means the two input files are identical. So now I'm actually fairly sure that I got everything done correctly. Alright, so I suppose it's time to turn it in, because I think everything is working out. Alright, yeah, so that's about it. I mean, that's the lab. Alright, so I just submitted my quiz. Let me get this window out of the way, because we don't really need to see it right now. And did I get all the points? Yep. On that too. Yep. So what is left for me to do is to actually submit the file, and I already checked to make sure that it is 100%, because the output is identical to the test driver. So this is kind of important. I think it's important. If I give you the tool to double check everything, you probably want to use it, because otherwise, if there's any difference between the correct output and the output of your program, there'll be points deducted, because there's this specification that tells you what the program is supposed to do, and there's also the tool to help you double check everything. Alright, let me see. Oh, so there are a few comments about this particular lab. It is longer, okay, I admit it is longer, But it is also a test. Okay, you can look at this as an assessment. I wouldn't call it a test, but it's an assessment of how well you understand the tool, and how well you understand the tool being Logisim, and how well you understand all the concepts, and not just binary addition concept, but also concepts in Logisim itself. Let me switch back to, oh, I don't have Logisim anymore. So for instance, the concept of a splitter, the concept of a multi-bit gate, all of those are important concepts. All right. I'm just looking at the mic level. It looks like I might be saturating the mic a little bit today in this particular segment. So I'm gonna double check a little bit before I upload it, but I think it's gonna be okay. Alrighty. So next Tuesday we're gonna talk about binary subtraction. So I would advise you to at least finish reading binary subtraction, if not beyond that. There's a chance that we can move on to beyond binary subtraction, but reading up to and including the entire binary subtraction module would be very helpful. Alright, I'll see you all on Tuesday.